Welcome. After learning the fundamentals of the analysis of the multi-component systems, today in this lecture we shall be solving some problems to highlight those methods. So in this we have the tutorial on the equilibrium in multi-component systems, and in this we shall be learning about the bubble point calculation, dew point calculation in multi-component systems and multi-component flash. So, first let us take an example of bubble point calculation. In this, we have to determine the bubble point temperature of an ideal solution having 20 mole% in pentane, which is labeled as component 1, and 40 mole% each of N-hexane and N-heptane, which are labeled as component 2 and component 3 respectively, and the pressure is 1.5 bar. The vapor pressure we will need to find out the volatility is taken from this particular equation, that is the Antoine equation, and in this the temperature is in degree centigrade and the pressure is in millimeter of Hg. So, this equation may be used to find out the boiling point at a given pressure or the vapor pressure at a given temperature. And the A, B, C values will depend on the particular component, and these values have been listed in this particular table. Here we find for N-pentane, hexane, N-heptane, the boiling points are given and the A, B, C values are given. Now, with these information, we shall proceed with the solution. First, what we do, we list out the molecular weight of each of the components and then find out the average molecular weight by summing up the product of the mole fraction and the molecular weight of each of the components, and we find this is coming out to be 88.8. Here, because the N-heptane and N-hexane has the same composition, so we are multiplying this 0.4, we are taking out of the bracket and putting their respective molecular weight. Now, we find that this average molecular weight is closer to M2, that is N-hexane. So, we choose N-hexane as the reference component. So, this is the way we choose the reference component in a given mixture by looking at the average molecular weight of the mixture. Now, once we have chosen the reference component, what we do, we find the boiling point of the reference component as the first guess for the bubble point temperature. So, in this case what we do, we add this 1.5 bar pressure as we take this as the vapor pressure, and we calculate the temperature from the Antoine equation, and we find that the value comes out to be almost 82 degrees centigrade or 355 Kelvin. So, this value is taken as the initial guess temperature. Now, what we do, we find the vapor pressures of the other two components at this particular temperature again from the Antoine equation, and we get these two values respectively for the other two components. So, here we now find the relative volatility, because in the problem we have been told that we may assume it to be an ideal solution. So, we take with respect to the reference component, that is component 2, we find out the relative volatilities first with for the N-pentane and then for the N-heptane, and we find these are the values of the relative volatilities. And looking at these values, we find that when N-hexane is more volatile than N-heptane, but less volatile than N-pentane, and this is expected because the molecular weight wise N-hexane lies between N-pentane and N-heptane. And now what we do, we find the value of the Kr, that is the reference value of the K, which is equal to K2, and this is the value of the Kr we find from the particular formula we have given earlier. And please understand that when we talk of bubble point, that means we are assuming that the given compositions are for the liquid. So, we use this formula xi into this alpha IR, that formula we use. So, 1 by summation of xi into alpha IR, that formula we use, and we get this as the value of the Kr. Once we obtain the value of the Kr, now we can again update these values of this P2 set, that is the vapor pressure of the N-hexane, and this we find as 1.3175 bar, that is about 1001.3 millimeter of mercury. So this is the updated value of the vapor pressure of N-hexane, that is the reference component. Once we got that pressure, updated pressure, again we go back to the Antoine equation, and at that particular pressure we find out the updated temperature as this value 77.85 degrees centigrade. And again with this value, what we do, we update the values of the vapor pressures of the other two components, and we find that vapor pressures are coming out to be now 3.5 bar and 0.7377 bar. That means what we are doing, basically we are updating the values of the temperature and the pressure by these iterations. So we have completed one iteration and we updated the values of the temperature and the pressures. Now with these values of the various vapor pressures, we now find out the K1, K2 and K3 values like this, that we know that P sat by P is the K1. So that is the way we Ki equal to Pi sat by P. That is how we are finding the values of the various Ki's. And once we find the various Ki's, now what we need to check? We need to check that whether this Ki xi, once we take the summation of these things, this must be coming out to be 1 and this is coming out to about 1.014. Now whether we should stop here or whether we should proceed beyond that, it will depend on the accuracy desired by the user. So somebody can say that we can take this 77.85 as a solution for the bubble point temperature. Otherwise, if we need more accuracy, then we have to repeat this whole procedure again with these values of this. With this, we can again repeat the procedure, like we find the value of alpha, Kr, again from that the Ti's T value, and then Ki, again we find the value of the K1, K2, K3, and again keep checking up this particular summation, and that is how we will carry out the iterations. In similar fashion, we go to a dew point calculation problem. In this, we have been asked to determine the dew point temperature in a mixture with the mixture contains 15 mole % of N-butane, which is labeled as component 1, then 15 mole % of N-pentane component 2, 20 mole % of cyclohexane component 3, 20 mole % of N-hexane component 4, and 30 mole % of N-heptane component 5. This is the component 5 and at 1.5 bar total pressure. And we are asked that we can assume the Raoult's law like the earlier question, and we have been given this Antoine equation to find out the vapor pressures of the components. And these are the constants which are required to find out the vapor pressure of the various components, and these are the boiling points of each of the components. Now what we do, we again find out the molecular weight of each of the components, and from that we find out the average molecular weight of the mixture, which is coming out to 83.6, and we find here that this value is coming closer to this particular value. So we again, in this case, we choose cyclohexane as our reference component. And once we have chosen this reference component, what we do from the Antoine equation, what we do that we find out the boiling point of cyclohexane at 1.5 bar, which is coming out to be 94.5 degrees centigrade or 367.5 Kelvin. So this is our initial guess for the dew point temperature. And from this we find out the values of the vapor pressures of the rest of the components at this 94.5 degrees centigrade, and we find these are the values of the vapor pressures of the various components from the Antoine equation. We use these vapor pressure values to find out the value of the relative volatility like this, and we find out the relative volatility of all the components 1, 3, 2, 3, 4, 3 and 5, 3, because 3 is the reference component, and these are the values of the relative volatilities. And then from this we find the value of the Kr, and again we use this formula, that is the summation of Yi by Ki. So this summation formula we use to find out the value of the reference K value, and from this we update the value of the vapor pressure of the reference component like P into Kr, and we find this is the updated value of the vapor pressure. And with this vapor pressure value, what we do, again we go back to the Antoine equation to find out the second updated temperature value by finding the boiling point of the reference component, and that boiling point is coming out to be 86.22 degree centigrade. And with this updated value of the boiling point as a second guess of the temperature, we find out the values of the vapor pressures of each of the rest of the components, and we find these are the values of the vapor pressures of the components obtained from the Antoine equation. Once we have found these, then what we do, that we find the values of the K1, K2, K3, K4, etc. So, we find these values and we find that this particular summation we do, that this summation should coming out to be 1. Now, again depending on the accuracy desired by the user, we may stop or we may continue the iterations to keep updating the values of the temperature. So, this is the procedure to find out the value of the dew point temperature. In the next problem, we shall be looking into the multi-component flash distillation, and the problem is stated like this, that we have a mixture of 20 mole % of N-hexane component 1, 40 mole % on M-heptane component 2, and rest of it, that is 35 mole % of N-octane, that is component 3, at 400 Kelvin and 2 bar pressure. And first we have to figure out that whether the mixture will separate into two phases or not, and if we prove that yes, it can be separated in two phases, only then we can calculate the amounts and the compositions of the resulting phases, that is liquid and vapor, from this particular feed. And it has been mentioned that we may assume the solution to be ideal. And once we say that, then again we will be using the Antoine equation, and we just list out the values of the A, B, C for the Antoine coefficients. Now, going to the solution, we find again the molecular weight and the because we are being given the temperature, so we can directly find out the vapor pressures of each of the components, and these vapor pressure values will be taken to find out the K values of each of the components. And once we find the K values, what we do, that these are the composition of the feed, and we have been told that if we find this Ki into Zfi summation and Zfi by Ki summation, we take the summations, and we were told that if these two are coming out to be more than unity, then we can say that the phases will be splitting into two phases. That means feed will split into two phases. So, these two conditions must be satisfied simultaneously to ensure that the feed splits into two phases. So, after ensuring that feed is going into two phases, now we are ready to do the rest of the flash calculations. For this, what we do, first we find out from this particular equation we derived earlier, we use this equation which is coming from the material balance and the equilibrium relationship, and here we know that the F represents the ratio of the liquid to vapor flow rates, and we rearrange the equation and we get, if we rearrange it, we will get a cubic equation like this, and we will find in this cubic equation you can easily find out the values of these A, B, C, D, etc. will be coming out to be like this. Now, we find here that it is the 3 means the F for this is the A value, this is the B value, that is the F square, then F will be this value, this C, and D means F to the power 0, that means without any power to F, we find this is the value of D. Now, once we find the value of D is coming out to be 0, then we can easily see that F equal to 0 will be one of the solutions of this particular equation. Okay. So, but F equal to 0 is not acceptable, that means that would mean that there is no splitting of the feed. So, we will not accept F equal to 0 as our solution. So, what we find that we reduce the order of the equation by 1 and it becomes a quadratic equation, and this quadratic equation can be solved easily. One of the things is 0, which is discarded, and the other two roots are coming out to be one positive and another is negative. Now, negative root is not acceptable, so it has to be positive root. So, the only solution for this one is 0.2642, that is the positive root. Now, once we know the value of the f, then we can easily solve for the rest of the things. This f, as I told you, this ratio of the liquid to the vapor flow rates, and then we use this formula for finding out the vapor composition and the liquid composition, and once we plug in the values of f and the ZFI, and we find these are the values of the vapor mole fractions and the liquid mole fractions of these components. So, this is how we are able to find out the ratio of the flow rates of the vapor and liquid and also the compositions, and this problem may be extended also to know the say vapor flow rate or the liquid flow rate or both of them if we specify one of the components. Okay? So, this is how we are going to solve the flash problem. More can be known from these reference books. Thank you.